privilege of having a great keynote address to be given by Professor Cliff Mass from University of Washington. I think many of you are familiar with Cliff. Cliff has been around for a long time in this field. He started out at Cornell University in physics and actually worked with Carl Sagan, which is a cool fact, and got his PhD at University of Washington. And then went over to University of Maryland for 3 or 4 years before going back to University of Washington, where today he's a full professor in the atmospheric science department, right? Yes. He has worked on many things over the years, has more than 160 peer-reviewed publications to his credit, and is an expert in, again, many things, for example, the West Coast phenomenon, such as orographic precipitation, coastal searches, the Puget Sound convergence zone, downslope windstorms, and various local winds. They also are involved in NWP runs and computing, and they run, I guess, the most extensive local high-resolution prediction system for the Western United States. So that's pretty neat. Many of you are perhaps familiar with Cliff's blog, which is, I think, widely read and appreciated. And I actually was not aware, but he also has a podcast. So do check that out. Cliff has kindly agreed to give a keynote on RO and 2 weather prediction revolutions for us today. So please welcome Professor Mass. Thing. You kind of have to point it at the screen.
Okay, and to advance the that advances
the big button.
That's advances it. Okay, thank you very much. Well, you may be going to a second-rate baseball game tomorrow, the bottom tier, but that's not true of this group, and it makes me a little bit nervous because, as you may know, I'm not an RO scientist. But I know a lot about you, and the subject area that I work on, numerical weather prediction, is pretty close. So perhaps I'll have some information that might be useful to you. So let's get started. Well, my talk today is going to be about RO and the 2 weather prediction revolutions, and you've been involved with one of them. So let's talk about that. So believe it or not, and that's what I'm going to suggest, that numerical weather prediction has experienced 2 revolutions during the past several decades, 2 of them. And one of them you have been very important to. So the RO community has played a big role in the data acquisition and data simulation revolution. I mean, you've helped provide massive amounts of data that has helped revolutionize weather prediction and weather observation. And I just have a little bit of the RO observations down there. But it's just not you, it's the satellite community in general. So there has been an extraordinarily important satellite-driven increase in global forecast skill it's been going on for a while, but the key period was approximately the mid-1990s to approximately 2009. And here's a figure that's, very, very well known. Let's see if this laser works here. Yeah, it works. Wow. This is from 1984 through pretty much today. Shows you the anomaly correlation, which gives you an idea how good the large-scale forecast is. 1's at the top. And you see the story of EC versus NOAA, okay? This is, of course, embarrassing to all Americans, and I've written extensively several papers on this topic about why the United States is behind the Europeans. But I won't get into that here. Okay, but the key thing is, well, the Europeans are better than the National Weather Service, that's for sure, and there's been an increasing skill. But if you look carefully, the big increase in skill was in a relatively limited period of time, from the mid-1990s to maybe 2008. I mean, that's when the big increase happened, okay? All right. This is another famous figure. This is from the European Center, showing the skill of day 10, 7, 5, and 3 over time. And you see that the northern hemisphere is on the top line of each of these colored panels, and the southern hemisphere is the bottom one. And it's going up. The big increase was in that crucial period from the mid 90s into the 2000s. So you see that. But the other thing you see that's just extraordinary is the collapse between the northern hemisphere and the southern hemisphere. That's a real sign that it's the data that was doing it, right? And so when we started the period, the southern hemisphere was far less skillful than the northern hemisphere. But by the end of this satellite data revolution, they were together. I can show the same story in a number of ways, and I'm swiping a lot of graphics from the European Center. This shows you the number of days of predictability, and predictability is when the ACC drops to 80% for 500 hectopascal heights. And I know it's hard for you to read, but it's 1998 through 2024. Number of days predictability, 8.5 at the top, 4 at the bottom. And there was, in that period in the 90s, this tremendous increase in the number of days of predictability. And we see that in the northern hemisphere and the southern hemisphere. It's amazing. Something really special happened during that period. Well, I can show you these large scale statistics, but I'm a West Coast meteorologist at heart, and the effects of more data from satellites and from you folks and better data assimilation had an extraordinary effect on prediction of major storms hitting the West Coast. Before 1990, every major storm was poorly forecast. I mean, really poorly forecast, like sometimes not forecast, okay? And probably a great example of this is the greatest storm, the greatest tropical storm ever to hit the United States, anywhere in the United States. And that was the famous Columbus Day storm of 1962. Some of you may have heard of this storm, okay? Maybe not, okay? October 12th, it was a 995 low. If this storm hit today, it would be 30, $50 billion of damage if it hit today, okay? Well, that storm, and I have this is from some publication that shows you the low coming up the coast. The day before, it was not forecast. Zero forecast. If you read the Seattle Times the day before with the forecast, they told you it was a great day to get out there and you could take your hike or whatever, okay? It was not forecast the day before. And in fact, interestingly enough, people like myself have gone back and tried to redo it using modern weather prediction systems. So I've used WRF and MPAS. I've tried to rerun it, okay, using reanalysis grids, okay? But I couldn't get it right. No one could get it right because the data was simply not there, okay? We couldn't forecast these great storms. And this is true of many other storms. Just to give you an idea of the observations that we had variable in 1962, I don't know if you can see this analysis, the West Coast there, there's a few ship reports, and that's about it, right? We didn't have the satellite data then. Okay, but the magical thing is once we got the data from the satellite community and we learned how to assimilate it, after around 1995, every storm was forecast accurately a day or two before. I mean, every storm. And a classic, this is a storm I remember vividly. This is the Hanukkah Eve storm of 2006. The models just hit it days before, okay? And this is not the exception. Okay, so we had this tremendous increase in skill. And RO satellites played a role, particularly at the end of that period. You know better than I do when RO data became available. So after approximately 2007, you guys were making a huge contribution, and you can see this in a number of ways. One of them is one of these. This is a figure from the European Center produced of the contribution to different observing systems. Some of the other satellites, AMSU, was number one, but GPSRO, I showed there with the arrow. It's right. It's up there with the leaders in making a contribution. And here's another one from 2011. It's the same story. Okay. Okay, and you can look at those statistics, but the improvement of NWP as we get into the 2000s by RO data is documented in many papers, some of them written by people in this room. Okay. And even, by the way, even check AI. I want to make sure I've got the answer right. I don't do a talk these days without having AI check my work, and it includes the same thing. So we know this has to be reliable information. Okay. But okay. So everybody, you can all pat yourselves on the back. The satellite community can too, the data simulation community. We had this gigantic improvement from 1990, the mid-1990s to the 2000s. But then we got into what I call the Great Plateau, okay, where the skill from both the European Center and NOAA starts leveling off, okay? This is the anomaly correlation of the Northern Hemisphere. Okay, Southern Hemisphere is the same. I call it the Great Plateau. I don't know whether you people should consider this depressing or not, but we had the Great Plateau, a skill just going up a little bit. Okay. Okay. So the question I'm going to ask, does the Great Plateau mean that actual forecast skill at particular locations, did that stagnate as well? Okay, the Great Plateau, that's global, it's large scale stuff. But is the forecast here in Denver or in place in Europe or in China, did that plateau as well? Okay, what do you think? I get some uncertain. Some people nod, some people shaking their heads here. Okay, the answer is no. Skill continued to go up, and the reason for this is that there was another NWP revolution that went on. Okay. It occurred and it really snapped in as the Great Plateau developed, okay? So there's the RO and satellite data revolution, you guys are all involved in this. And there's another revolution, okay? Okay. It's a revolution that would allow mesoscale local forecast skill to increase. What was that revolution? What do you think? What was that other revolution? Everybody's quiet here. This is supposed to be the interactive part of the talk. Well, okay, I'm going to give you a hint. And I got two of the people in the room here. Bill Quo, which is right there, Rick Anthes, they played a major role in both revolutions. Both of them, okay? They're super revolutionaries, okay? Anybody want to guess what that revolution was? Yes, this was a person who knows what they're talking about. Yeah, the high resolution prediction revolution, right? That's the other revolution that came in. And during the past 2 decades, model resolution and physics as well, improved substantially, and that allowed a much more accurate simulation of mesoscale features. It allowed a better downscaling of the large scale flow that you've improved down to the mesoscale. And just some of you are familiar with this, but in the US, global models went from about 100-kilometer grid spacing in 1995. I'm old enough to remember those days, okay? Bill does too, to around 13-kilometer grid spacing in 2020. And that's global models. For the national, the regional models went from about 50-kilometer grid spacing down to 4 kilometers in the same period, okay? And so in some sense, you're going to a baseball game. You should have gone to a football game, okay? It would have been better for this talk. But in some ways, there was a handoff in terms of pushing forecast scale. You had improved global data simulation prediction. That was the starting point. You gave us in the mesoscale community this tremendously improved global prediction. And high resolution prediction then took over and kept the skill going up rapidly. Okay. Just to show you how far we've come, this is the state-of-the-art prediction of precipitation over the United States in 1995 from the famous NGM model, okay? A lot of you don't know about this, the nested grid model, okay? This is the precipitation over the western United States. You see the shading there? This was a precipitation. Do you see all the structure there? This was state-of-the-art in 1995. It's embarrassing to admit this, okay? But it's true. Here's a blow-up. Here's over the Northwest. Okay, I'm a Northwest meteorologist. There's the terrain, and there's the prediction of precipitation. You see the terrain effects? Maybe they weren't there. I mean, this is I mean, it's not that long ago, folks. You know, anybody in the room with gray hair can remember this period. Just for this talk, I reran WRF at 100-kilometer grid spacing it shows the 24-hour precipitation ending, 28 February 2024. This shows you what 100-kilometer grid spacing for 24-hour precipitation looks like, and that's what 12-kilometer looks like, okay? There's no effects of terrain, no effects of almost anything except the large-scale flow in 100-kilometer grid spacing, which we had, that's the mid-90s, folks. And the right is 12 kilometers grid spacing. That, the global models are all at this rate. The global models are at this resolution now, or better, right? The European Center is 9, right? The Weather Service is 13. And the terrain stuff snaps in. But it's even better than that, with higher resolution. You got things like frontal collapse and frontal circulations, downslope windstorms. We got those, we nail those now, okay? Convection starts to be resolved. Diurnal circulations are resolved, much, much more. Just to show you, each day I'm amazed when I look at some of the forecasts. Just to give you an example, this is relative. This is 2020. On the left shows you radar. This is a radar coming into the West Coast. And you can see the red lines with a higher reflectivity. This is what we call a narrow cold frontal rain band, and it has this corrugated structure. Okay, I don't know if you've heard about this, narrow cold frontal rain bands, and that was observed. Peter Hobbs first described this back in the 1970s. On the right is a WRF simulation. We're running real time, 1.3 kilometers, and there it is. It's almost perfect. So we not only have the resolution to find these fields, but the large scale flow is good enough that we can downscale to this kind of structure and get it right. I mean, this is unbelievable achievement we've made. Okay. Well, I showed you some qualitative stuff. Is there objective evidence of the second revolution that took advantage of your revolution? Is there evidence? Well, it's actually not. There are not many papers on this. It's really interesting. This is something that the younger people we need to write some papers on this second revolution. This is I'll show you. This is from the Weather Prediction Center. NOAA has a Weather Prediction Center, and they actually say you can actually get some long-term information. This shows you this is over the United States maximum temperature. This is the mean absolute error. And this is from 1971 to 2023. What I want you, so this goes through the whole period that I showed you before. You notice that the skill didn't stagnate. The error went down even after the satellite revolution occurred, right? So the forecast still continued to get better. His minimum temperatures is the same thing. You really want to be impressed. These are threat scores for a half an inch during a day, and the threat scores are getting better and better, even in recent years. You really want to be impressed for 2 inches or more heavy precipitation, more extreme things. We're getting better and better and better. And just to have fun, I just plotted some of the mean absolute error for model output statistics for cities like Phoenix and others. And you can see it as well. The skill has gotten better and better in recent years, even though the large scale, anomaly correlations have kind of stagnated, right? It's 2 revolutions going on. Okay. If you want to see a stunning example of how far we've come, let's consider the greatest weather-related disaster, probably, of the last several years. And you know what I'm talking about. What happened on August 8th, 2023, the downslope windstorm and wildfires that hit central and western Maui, particularly the town of Lahaina, and it killed 100 people, resulted in $3 to $6 billion of damage, okay? This is one of the greatest weather disasters of the last several years, okay? And there's a picture, look, this is Lahaina right here close in, and you can see the West Maui Mountains there, and you can see the absolutely destroyed town of Lahaina. Okay. Now, this wildfire was driven by extremely strong winds. And the best estimates we have, and here's a map here, the arrows pointing to where Lahaina is, that the winds gusted to 60 to 80 knots in and east of Lahaina, okay? Well, here's the shocker, maybe it should be a shocker. The forecasts were almost perfect. The 24-hour forecasts were almost perfect. This is a WRF forecast that I ran, but the HER model did the same thing. The red shows you where the strong winds were, and the model almost perfectly predicted the strong winds that were going to descend down into Lahaina the day before. But now the real shocker, well, before I show that, it was a downslope windstorm. This is a vertical cross section through. The shading shows you the winds. I don't know if you can see the high amplitude wave. So this downslope, it was a downslope windstorm associated, with a high amplitude mountain wave. That's what happened. And that's what was predicted almost perfectly the day before. But here's the shocker. There was almost no loss of skill 6 days ahead. So up to 6 days ahead, we predicted this thing perfectly. So this is another issue that we have gained tremendous skill, and society is still unable to take advantage of it, right? That's another challenge that all of us have, okay? So as much work as we do, if we don't get the last mile that people use our forecasts, of course, that's an issue. So I want to stress the two revolutions made this possible. I want to, I got to stress this. Excellent large-scale observation and initialization, better data, and the ability to do the data assimilation better, that set up the large-scale flow. And then the models now can do the downscaling almost perfectly. Okay. And by the way, I should tell you, this is not a one-off. I can show you a dozen of these kind of simulations, a dozen. We get it perfect the day before. Another example, which I'll mention briefly, is the other great weather disaster on the West Coast, the Camp Fire that destroyed the town of Paradise. And just for those of you who are not from the West Coast, the shaded area is where the fire was. There's the Pacific Coast over there. This was another one where the models predicted perfectly the days before what was going to happen. Okay. So anyways, we got two revolutions. Your revolution, wrong way. How do I go back? Lower button? I don't want to, okay. I don't want to give away my best stuff. All right. Anyway, when we get invited to give a keynote talk, you're expected to look into the future. I know Bill would want his money back or something if I didn't do this, right? So, right, Bill? So anyway, so I'm going to do that. I'm going to get a little edgy now. I was asked to be a little edgy, so I'll do that, okay? Well, here's something that's edgy. My community, the numerical weather prediction community, which I'm definitely a member of, has not caught up with you folks. We have not caught up with the improved global analysis and data assimilation that have been made possible by your community and other satellite communities. So this is the classic dog chasing a car. That's what, that's you in a nice way. And that's me and other people like me, the weather prediction community. We're chasing you. We haven't caught up with you yet. Okay. We haven't taken advantage of what you are giving us. So why are modelers like me behind you? Okay. Why haven't we caught up to you? That's an interesting question. Okay. One reason, and I can give you a number of reasons. One reason is our models are still very flawed. Okay. And a good example is most global models parameterize convection. And let's be honest with each other. Convective parameterizations are all problematic and inadequate. Every single one of them, they're a kludge. They do something, but they're not good at it, okay? And there is extensive evidence that convection allowing resolution in global models is revolutionary. And that if you can run your global models at a convection allowing resolution, there is so much more skill to be derived. And I'm just not saying this, several people worked on it. I've worked on this. I had a project where I ran MPass at convection allowing resolution for 1 month simulations. Okay. And with Nick Weber, my ex-graduate student, got his PhD at UW. And so we've done a series of 1 month forecasts at convection allowing resolution. And the results were extraordinary. We got convection right, propagation of convection right, things like the MJO. We got that right. Just to give you an example, his trim showing you reality in the left, MPass running at 12 kilometers is the middle, and then at 3 kilometers, wow. But it's more than that. We actually verified how good the forecasts were going out a month. And this is it over here. You can see week 1, 2, 3, and 4. This skill increases vertically. And basically, the first week, it didn't make that much of a difference. By the time you got to weeks 3 and 4, the 3 kilometer MPass, which is the red, was doing a hell of a lot better than the 12 kilometer MPass was. So there was tremendous skill. We've seen this, by the way, on the mesoscale as well. So we know that if we get rid of convective parameterizations, we have a lot more skill, and skill that we could use to take advantage of what you're giving us. Okay. So it's only a matter of time. It's only a matter of time before all global NWP models will be run at convection allowing resolution with explicitly modeled convection. It's only a matter of time. In fact, how could we not do it? Okay. Because the skill is there to be taken. And when we have that skill, we can take much better advantage of the satellite data that you're giving us. By the way, but there's something else. There's more proof that current models are not taking advantage of the potential skill that you're providing. There's other proof of this other than the runs that I've showed you. And one of them is the implications of machine learning. Okay. So the machine learning NWP has gotten a lot of press lately, right? Everybody's read about it. There's been paper after paper. Everybody's all excited about this. Okay. So what the machine learning systems NWP implies that there is a lot. They're starting with the same initializations. They're implying what I just told you before, that there is a lot more skill to be squeezed out of our current initial conditions. Okay, a lot more. And so I think a message of all this is that today's physical global models, the American UFS, the European Center model, you name it, have major deficiencies in physics and other parameterizations that prevent them from deriving the maximum skill from the improved descriptions of the initial state that you're providing. Okay, I think that's it's pretty clear, folks. By the way, the European Center has a lot of these shows these statistics for their AI version, the AI model versus the physical model IFS. Okay, and here's an example for the northern hemisphere extratropics. This is an anomaly correlation. Northern hemisphere, again, 100% at the top there. This is forecast days, and I know it's hard to see, from 1 to 10. And the physical model is the red, and the AI model is the purple. And clearly, at longer leads, the AI model is doing substantially better. Okay, the same thing is true in the southern hemisphere. But here's the interesting thing: have you looked at their statistics in the tropics? That's interesting. In the tropics, the AI model is doing much better, okay, compared to the northern hemisphere. So I have the comparison here. So tropics is on the left, northern hemisphere is on the right. You can see the differences. And AI NWP is relatively more skillful in the tropics than it is in the mid-latitudes. Why is that? You can guess why that is. The tropics, one reason may be because the tropics is a lot more convection, right? And the traditional models are not very good with convection. Okay. So, I think the implication of AI, it may not be simulating direction directly, but it's better at getting the aggregate effects of convection, giving a certain synoptics. So an important point I want to make is either convection allowing model resolution or using AI models will allow global NWP to use the improved initial state that you and the satellite community are providing. Okay, we have a lot more skill that is potentially possible. Okay. So I like dogs catching up to cars, obviously I got a bias here. Okay. So this is something for you, a warning to you. Eventually, either with AI models or with better physical models, we're going to catch up to you. Okay, we're going to do it. So the dog is going to catch up to you, folks. So there's good reason that you're working to get more satellites up there and improve data assimilation, because otherwise we will catch up to you. It may be 5 years from now, but we're going to be on your fender before you know it. By the way, one final note. Most AI, virtually all AI at NWP is trained on analyses like the ERA5. Okay. If observations are dense enough from RO and other satellite assets, eventually AI NWP can be trained directly on observations or gridded versions of the observations. It's kind of an interesting thing, This might be the next generation of AI models, right? Directly training on higher density observations. Okay, well, I've gone on long enough. Let me just summarize. These are my take-home messages to you. Increased satellite assets like RO, led to a rapid increase in large-scale forecast scale in NWP. And that was particularly true from 1995 to around 2008, okay? Followed by the Great Plateau. Mesoscale forecasting skill continued to increase rapidly because of improved resolution and improved physics. Let's get back to the dog. Operational NWP has not caught up to the potential of the current analyses. It hasn't. But I suspect it will. Between convection allowing NWP and AI NWP, eventually we're going to catch up. So you're going to have to keep ahead. And so just for the young people, I just want to leave a certain message with how far we have to go. And I love this Winston Churchill quote: "Now is not the end. It's not even the beginning of the end, but for us, it's perhaps the end of the beginning." And so we are at the beginning still. So thank you very much. It's good to talk to you. And I don't know how we want to do this now. We have comments, questions. Who's moderating this? Are you moderating? You can say something. You maybe want to use the mic.
Ask that you go to the microphone.
Yeah, so I think thank you for a very inspiring talks.
Thank you.
Enjoyed it very much, and I think we all know that radiative occultation improved temperatures in the upper troposphere, stratosphere, but there is a lot of water vapor information in the lower troposphere, and it doesn't make it into the analysis and in the forecasts. I understand it's difficult. There's potential reflectivity bias in the lower troposphere, and weather centers need to be conservative in order not to destroy the solution. But there's a lot of water vapor information which is not used currently.
Yeah. Well, that's a very interesting comment. Rick, yes.
Well, hello.
Yeah, it's working. Yeah.
I must say you've mellowed in your golden years.
Mellowed?
Mellowed. You said at one point you were trying to be a little bit provocative or something, but I've heard you be a lot more provocative. My question is seriously do you think, or what do you think the added value of all these satellite observations, especially RO, is to initialize the mesoscale model that adds value beyond just better large-scale forecasts? In other words, what's the additional value of modifying the initial guess for the mesoscale model by the same observations that were used in the global model?
Yeah, I don't know the answer to that, and I think that's an extraordinarily interesting question that I think needs to be explored. So no, I don't have the answer to that, but you're on a very important question. I mean, obviously, RO satellites are less useful in the lower atmosphere, but I don't know. Bill.
Well, thank you, Chris, for a very inspiring talk. I do wanted to point out, thank you for giving us a lot of credit. But I also wanted to point out that, you said that the rapid increase was from the mid-90s to 2009.
Or in that period.
And you know that the real RO contribution to NWP actually started maybe about up to September 2006.
I know.
After COSMIC was launched. So
well, that's why I was being careful, because the RO came in at the end of that period. So we have to give credit to the rest of the satellite community. That's true.
Well, and I think one point to make is that it depends on what do you use as a major stick. Then you're using the anomaly correlation, and those obviously mostly large scale.
Right.
As you pointed out, continuing improvement is actually on the mesoscale. 2 points to make is that we actually have been doing research and finding that actually the RO can help improve mesoscale prediction. We are studying like the convection over Taiwan during the May-U period.
Right.
As a combination of topography and also the frontal movement, you actually, if the better definition of large scale, can actually improve convective forecast. So it is some situation we can see that.
There are some case studies that indicate that.
And the second point I want to make is that perhaps you have not been very much involved yet, but I wanted to point out that we have the polarimetric radial quotation that started with PARS. And this recent study also shows that we can use that observation to evaluate microphysics. Because, for example, WRF have 7 different microphysics schemes, but we don't know how to evaluate those schemes, right? But I think results showing that it's possible to be using that kind of observation to improve the mesoscale prediction.
No, that's an important point. And if you want something more controversial, I'll do that in the coffee area. I can provide that if you need it. Good, go ahead. Yeah.
Yeah, so I'm going to thank you very much. That was a great talk, really exciting. And I want to say something sort of CGMS perspective, the weather agencies. So from a weather agency perspective, if they look at these large scale metrics, the value of satellite data is plateauing.
Right.
So they would question, well, why should I invest more in satellite data? So I think the point you're making is we have to connect that. But I don't think the agencies have done that. I don't think they've connected the improved mesoscale predictions to the fact that, is that based on satellite data, or what is the answer there? Bill was making the point, and Uli was making the point. And, we should keep in mind that also for those cases, we are not doing a good job of using the RO data in the lower atmosphere.
Right.
And as Uli said, very hard problem, but, these are related perhaps. Thank you.
Well, if you want something controversial, okay, I'm going to do it. That's what Rick wants. It's the verification provided by major international NWP centers is embarrassing. I mean, if you go to the National Weather Service verification page, they have these anomaly correlations, but there's, you go to the MEG site, there's nothing about higher resolution verification over the United States or any place else. So this is a tremendous hole, for some of the young people here. I mean, no one's done the verification at high resolution. This story is not being told. It's not in papers. It's and national NWP centers are not doing it. So this is something that needs to be worked on because people don't understand the story. We have come so far and people don't know it. And people not knowing it has a big implication. That's why places like Lahaina burned down, because people don't appreciate what we can give them. And people are dying as a result. Is that controversial enough? Or I can rev up more. Go ahead.
Yes, this is Ben Ho from NOAA. I think it's a very very difficult to really quantify what actually improved the focus scale from 1996 to after.
Right.
Because there are so many things happen, right? Like AIR's high resolution data, high resolution infrared data,
right?
And then IRC and many others, and also increase in data set. And how RO really play a role is also hard to quantify because there's so many things happen.
True.
So if let's say NOAA people will come and it will say, oh wow, it's infrared, and then microwave people will come, oh, got to be microwave, right? So I think it's a very interesting to see that is a keep on increasing over that period of time, and then even certain period of time when RO, for example, customer one, actually the sample number are decreasing, or the total number are flat. So I think maybe there's one more things is the data simulation skill may be increasing of their approach, 3D VAR or something else. So that's my personal opinion.
I mean, there's these kind of figures you see right and left, right? And the question is how reliable do you feel this kind of evaluation is? And they all show the satellites being on top and RO being, maybe not the top, but being up there. So yeah, go ahead, please.
Yeah. So very interesting talk on many levels. I wanted to make a few comments.
Please.
On the downslope winds, I used to be at University of Arizona. Now I'm up here in the Boulder area.
Right.
There was another example of what you said about the downslope winds. There was actually a forecast made using high resolution WRF to resolve all the topography in Arizona. And there was a movie about this. Actually, there was a fire that killed 19 firefighters because they went in the afternoon, they went across an open area that they shouldn't have. That was forecasted a day ahead. That they couldn't get, there was no way to get the information through the human infrastructure to let the people know, the firefighters, and they did the exact wrong thing and were all killed. So I don't have a solution to that. I'm just saying I've seen another version of that you're talking about with the downslope wind.
Right.
So that's one thing. Another question I had on the resolution of the convection. So you're running MPAS at 3 kilometers. I guess I'm a little surprised that's good enough resolution to get the convection adequately, because I thought we had to go to smaller resolution than that. But I mean, the fact that I'm astonished at the way you can get the small scale convection and you can see the MJ, it allows the model to get the MJ, the large scale, this thing that people have been mystified. Why don't the models get the propagation speed? It's astonishing to me. If you get the small scale right, the organized convection then behaves, realistically. So two more things in it. I do want to say that RO in the lower troposphere, I think there's a lot of potential there with the high signal to noise. I mean, this is what our company does, and I'll show this on Tuesday. But there's a lot of information content down there. It's very noisy because of convection.
Right.
But that's also a signature that has information contained in it, which may be AI. And my last point was, I agree, there's a lot of information in the RO that's not getting into the NWP, and maybe AI can be the mechanism to extract that. So anyway, those are my 4 points.
Those are very well taken. There's a comment.
Okay, one more comment. Of course, we know the large impact of the cosmic data on NWP, but the impact of RO actually started a bit earlier with the CHAMP satellite.
Right.
And it was amazing how the maybe 200 profiles per day from this single satellite had an impact in areas where the traditional observations were not so good, around the tropopause, for example, or over Antarctica. So nobody at ECMWF expected that this small amount of data could have such an impact, but
Right.
they were just at the right place with the right vertical resolution,
Right.
basically.
No, that's absolutely true. Yeah. I think there was another comment there.
Yeah, just a quick point on the plateau. So I don't think it's any surprise that on a diagnostic plot like that, there will be a plateau because
Right.
your anomaly correlations can never exceed 1. So I would suggest a different metric the closer you
Right.
get to 1, and that is to ask a question such as, how far into the future can you predict with an anomaly correlation of 1/2 or something like that?
Yeah.
That actually has an indefinite horizon.
Right. No, I agree with you. And I think, we need better diagnostics, but this anomaly correlation stuff is what's typically used, but it's not good enough. How much more time do we have for the organizer? Okay.
Okay,
Go ahead.
Thank you very much for a very interesting talk. My question is, as the model resolution improves, what sort of measurements would make more of an impact for the forecast? Would higher resolution measurements be more valuable? And as far as radar occultation is concerned, obviously each radar occultation has limited resolution, especially spatial resolution. If we can get sort of a cluster distribution of radio occultation that happen near each other, would that be variable as the model resolution improves?
Well, as a West Coast meteorologist, clearly having higher resolution and more lower tropospheric detail is what we need. Okay. Now we're getting most cases, but there are some cases that we're still missing. When we don't have quite the resolution of satellite data, and we're messing up. And I'll give you a good example of failure. I've talked about a lot of successes, but there was a failure very close. There was a downslope windstorm here that caused a major fire just south of Boulder, right? That was not a great success days before. And that was an example where there was relatively fine scale structures over the Pacific that we were missing. And we were right along the edge of where the jet stream was. And those small errors in that case caused a fairly substantial forecast failure for that case here near Boulder. So I think lower troposphere, more detail, still can have benefit for these difficult cases.
Hi, my name is Katrin. I'm from
Hi.
Eastern Obrief. And as you've shown so many plots from us.
Thank you very much for your plots.
Well, yeah, so I just want to highlight, I think GNSO, I think we still not yet understand the whole impact of the data.
Yeah.
So now with, at the moment we are estimating around 10,000 occultations per day. And with this nice ROMEX experiment, we can see we get even more improvement if we triple or more than triple.
You've demonstrated that.
Yeah, it's in progress, the work in progress. But
okay.
So that's a very nice thing to show. Also, when it comes to verification, it's important to look at different scales, like spatial scales and different forecast days, how we improve things in this term. So I think there's still a lot of scope to see actually what the assimilation of GNSO data can do. So yeah, we are at the end of the beginning, I would say.
Okay. Okay. Oh, this comment there.
Yeah.
Oh.
All right.
Oh, Rick.
Quick comment, and then well, 2 comments. One is it's nice to see somebody looking at these high impact extreme events, because looking at the improvement in those anomaly correlation over the last year, getting a 0.01% increase in it's very hard to do. So that's one comment. It's nice we should be looking at some high impact.
We should,
tropical cyclone, big storm, whatever.
Yeah.
The other comment is that in spite of all the evidence of the value of RO, and RO being some of the latest slides of this type, and Neil Bowler may show shows that RO is even higher. It's in the top 1, 2, or 3, or 4.
Really? Okay.
Yeah. And it goes on, and yet there's still no international plan for a committed minimum number of backbone, so-called backbone of RO observations
Right.
to go on for the next several decades. We're still relying on kind of missions of opportunity and buying a few data here and there. And that's something that we all ought to work toward, is getting a sustained plan for a sustained high quality RO global, all local time observations of a number, something like the IROWG has been recommending for many years of 20,000 per day. But there's no commitment yet, our plan.
Right, and that's connected with there's no sort of global rational plan for designing an optimal, data assimilation, observing and data assimilation system. I mean, that's a big gap.
Yeah. Hello.
Right.
Thank you for this really inspiring talk. I liked it a lot. And so you reported on these two revolutions. So is the AI, so AI, of course, is a lot of under discussion. Is this the third revolution, or what do you think on that? The third revolution in weather forecast or whatever. So what is your opinion on that? I would be very interested to hear this.
Well, obviously it's a revolution. The question is it just a better way to do the global prediction? Is it better just because the physics and physical models are inferior, right? It's quite interesting, so it could very well be the third revolution. Yeah. So, okay. Well, I think we're done.
Any other comments? All right. Well, let's thank Cliff again. Thank you. So I think we finished slightly early, which is actually helpful. I think maybe that'll allow us to have a little bit longer lunch. So I'm going to suggest that we start back